Starting with the most advanced PDF extraction in the industry, I will bring up a Cypress part, a chip network processor, where we can extract the content from this flat pack diagram or very complex BGA diagrams, such as this 360-pin BGA map, or, as in this case, from a table or pages of table. I will begin the process by enclosing the area that I wish to extract. Selecting Build will build the PDF extraction template. Next, I will tag the rows which I wish to ignore on data transfer, such as these header columns. Or with the blue tag, I can tag in microprocessor datasheet groups of pins. Selecting Export, I'm now ready to transfer the content from the PDF datasheet to the Scratchpad spreadsheets. You will note several cells in red. These cells contain overbars in the original PDF content. Let's map these red cells to negation codes by applying an _L, N, or / characters. Next, let's tag the columns to give them very specific meaning, such as pin name, pin direction, and pin number. And if doing an FPGA design, voltage, standards, and banks. Once this is complete, we will transfer the content from the Scratchpad spreadsheet to the main spreadsheet. The main spreadsheet now contains the extracted content in the correct columns. Widening out the columns, you will notice that the bus syntax is contained in a single line. This will be fractured out during the checking process. You will also notice a host of accelerator commands to accelerate syntax mapping. We will use the direction code from string to automate out the direction code from the line containing the pin description. Next, I will check the datasheet, which will automate the fracturing of the bus syntax to each individual member of the bus. A second accelerator command will be used to automatically detect the pin function code, such as clock pins or negated logic. And a third accelerator command will be used to automatically create unique pin names. Checking the datasheet, I'm now ready to proceed to the next step, with 64 pins in the original spreadsheet. But what if there is an error? Suppose I accidentally missed a couple pins, or the datasheet contained errors. I will intentionally create an error by deleting and removing 2 pins, containing 62 out of 64 pins. Let's now move to the Footprint Builder, where we will build the footprint part and isolate the 2 errors introduced into the spreadsheet. Footprint Builder contains the most advanced set of header connector catalogs in the industry. Surface mount calculators include BGAs, CAPs, CFPs, CGAs, chip arrays, crystals, CQFBs, DFNs, diodes, LCCs and A's and LGAs, oscillators, PLCCs, QFNs and Ps, SODs, SODs, FLs, SOJs, Ns and Ps, SOTs, TOs, and other devices, including through holes, caps, diodes, fuses, inductors, LEDs, and transistor cylindrical, and other advanced calculators such as dual-roll QFNs. We will be modeling this part using an advanced QFN package. Selecting the QFN part and the default package. 2 options exist, either the user-defined manufacturer's recommended LAN patterns or the IPC 7351 standard, supporting the 3 tiers including nominal, maximum, and minimum settings. The User tab contains the user settings or corporate design rules, and the drafting settings contains the recommended drafting settings, configurable to each corporate standards. On the Component tab, there are the options for the QFN package, supporting pad shapes of rectangular, oblong, and D-shaped, and custom pad stack variances using the Pathback Calculator. Let's start by modeling the part using the associative editor. Clicking on the value directly on the screen, I will change the A nominal value to 11.5 and the B nominal value with a 0.2 tolerance to 11.5. Changing the number of pins on the side to 16 and 16, I will select Generate, where I have 4 DRC errors, each in the individual corners. This particular data sheet calls for a rectangular pad with chamfered corners in the individual 4 corners. We will use the Pathback Calculator to customize the 4 sets of corner pads. Bringing up the corner, I will create a variance for the first corner pad and a second variance for the second corner pad. Now that I've created two variances, I will modify those variance pads to contain chamfering on the opposing corners. Let's move to the Editor tab on the Pathback Calculator. Selecting the first variance, I will select the specific corner that I wish to modify and chamfer the results to 0.15. Next, I will select the second variance, or R11235 corner 2, and click on the Modify Shape button. Selecting the specific corner to modify and chamfering the corner to 0.15. Modifications are not limited to chamfering or rounding. Within the editor there exists a host of advanced shape editing commands for cutouts, moves, and bands to handle the most advanced shapes. Moving to the Mapping tab and clicking on the individual pins, I will replace the pins with the first variance. Clicking on the second set of pads on the opposing corners, I will replace those pads with the second variance. I've now replaced the four corners with the two sets of variant pads. Taking down the pad stack modifier, let's zoom in on the upper left corner. Rerunning the DRC check, we've now eliminated the previous DRC violations. Zooming out to full view and selecting Generate. Unlike previous wizard technologies used in the industry, EDA Builder and Footprint Builder are reentering. Reentrancy allows us to add modifications such as these four corner opposing pad stacks, and then selecting Generate to regenerate the part using the variance modifications to impact the final results, such as courtyard keep-out areas, placement boundaries, and manufacturing rules. Let's now add a 6.0 by 6.0 thermal pad, selecting Generate, and using the Reentering Calculator. And we can make modifications to that thermal pad by moving to the Pathback Calculator, bringing up the New Pad tab, and clicking on the pad type of a thermal pad with a paste mask or a via array. Clicking on the thermal pad with paste array, I will change the number of rows to 4 and 6 for the pattern, selecting Generate. Next, I will move to the Mapping tab, where I will perform the replacement. Clicking on the variant thermal pad, and clicking on the pad to be replaced in the original package. I will replace or swap the original pad with the newly defined variant thermal pad. I have now completed my PCB footprint package. Let's move back and annotate the symbol spreadsheet which we extracted during the PDF extraction to the footprint view. In that spreadsheet we intentionally created two errors. Let's isolate those errors by bringing up the graphical report and showing all terminals with missing pin assignments, pin 23 and 24. Let's move back to the symbol builder by configuring both and complete the symbol automation. I will first add back in the two missing pins and recheck the datasheet, now containing the original 64 pins. Now that we have 64 pins matching the footprint, let's move to the symbol partitioner and begin the symbol partitioning process. First, let's start by sorting by pin name and then pin direction. Next, let's select the interactive drag and drop, clicking on the pins in the spreadsheet and dropping the pins onto the graphical display. Selecting the I/O bus and moving it to the left side, and the CP bus and moving it to the right side, and the D bus, selecting the D bus and moving it to the right side. The A bus we will move, containing the output pins, to the right side. And notice with the clock and RW pins, as we select these pins from the spreadsheet, and drop them on the symbol view, all of the remaining pins are pushed down. To create a second part, let's create a new symbol using the next command. Taking the VDD and putting it on the left side, the VPP on the left side, the VSS on the right side, and the No Connect on the top. We've now completed the partitioning of the 64-pin fractured symbol set with cross-probing to the footprint from the symbol and the footprint back to the symbol. Bringing up the symbol view directory, we can arrange symbol fractures, moving the power to the last symbol fracture. Selecting the export, I will export the part to OrCAD Capture. Invoking OrCAD Capture, the part will automatically be read directly into OrCAD Capture. Selecting the library and viewing the part or the package view. I have completed the export of the part to OrCAD Capture with the part netlisting properties. Exporting the part to Allegro, I now have the completed PCB footprint part with all of the associated variances and pad shapes automated directly to Allegro.